welcome back. Today's goal of this lecture. Today I will see intermediate value theorem. In my previous video, I have defined intermediate value theorem on real axis. Today's goal of this lecture, today I will see intermediate value theorem on function of several variables. At first, just as a review and deep knowledge, at first I will say what is the intermediate value theorem on real line. But I will highly recommend you, if you don't see my previous video of intermediate value theorem, please see at first my previous video of intermediate value theorem. I have given the link in my description box. Then today's video would be so easy. Okay? At first, just as a review, let's see what is the intermediate value theorem on real line. Also for deep knowledge, I will some more example about this theorem. But in my previous video, I have defined and also defined many examples on this topic. Okay? Well, all of us know intermediate value theorem actually consequence of Bolzano's theorem, and actually Bolzano's theorem is let f be real valued continuous function on a compact interval ab in the real line R, and suppose fa and fb are opposite signs. Since fa and fb are opposite sign, that means fa times fb less than 0. If this condition hold, then there exists at least one point C in the open interval AB such that f of c equal to 0. Here, notice this condition is not necessary condition. If this condition hold, then obviously there exists at least one point C such that f of c equal to 0, but there exist many function which does not satisfy this two condition. But f of c equal to 0 means there exists a root, but there exists always one root. As for example, at first consider one fx which is defined from closed interval 0, 1 to R such that f of x equal to 1 when x lies between closed interval 0 and open half, and minus 1 when x lies between closed interval half to closed interval 1. Here the graph is such type. Here the 0, 1 interval, and here the point half. Here 1 and here minus 1. At the point 0 to open interval half, the value is 1, and half to close interval 1, the value is minus 1. And in this graph, there exists no point such that fx is 0, and this is possible. Here the Bolzano's theorem does not satisfy. There exists no point C such that f of c equal to 0. But there exist many functions in which the function is not continuous, but Bolzano's theorem has satisfied. Let's look such function. One function fx which is defined from closed interval minus 1 to 1 to R such that f of x equal to x when x lies between closed interval 0, 1 and minus 1 when x lies between closed interval 0 to minus 1. Here the graph of the function is look like fx equal to x when x lies 0 to 1 and minus 1 to 0 open interval 0, the value of the function is minus 1. Notice here the function has a discontinuity, but here at the point minus 1 the value is minus 1 and at the point 1 the value is 1. That means f of a times f of b less than 0. But at the point 0 the value of the function is 0. That means all condition of intermediate value theorem does not satisfy here, but there exists a root at the point 0. So these conditions are not necessary condition. This is sufficient condition. Now I will see the application of Bolzano theorem. This theorem, the name of this theorem is intermediate value theorem, and this is actually today's goal of this lecture. In my previous video I have defined this theorem obviously. Just as a review, today actually I will discuss the intermediate value theorem in higher dimension. Just as a review, just recall the Bolzano intermediate value theorem. The statement of this theorem is f be a function from closed interval ab to R which is continuous function, and if f of a less than y less than f of b, then there exists a point C in AB such that f of c equal to 1, and if f of a greater than y greater than f of b, then also there exists a point C in AB such that f of c equal to y. That means if f of a and f of b be 2 points of the function, then for any intermediate value of the function, for this value always I will get 1 point which have a value in the domain, because here the function is continuous. But this condition is not necessary condition. This is the sufficient condition. There exists many function who is not be continuous, but intermediate value theorem has satisfied. For example, consider fx equal to sine 1 over x when x not equal to 0 and 0 when x equal to 0. We all of us know this is the topological sine curve, and the graph of the curve is such type. At the point 0 this would be such type, and in this curve at the point 0 has a discontinuity, but if we consider C here, it does satisfy the intermediate value theorem, because for any C which lies between plus 1 to minus 1, for this C there exists at least 1 point in the domain such that f of x equal to C. This condition is sufficient condition. If this condition holds, then there exists at least 1 point C such that f of c equal to y. But there exists many function which not be continuous, but intermediate value theorem has satisfied. Obviously this proof of this function theorem is use of Bolzano's theorem. For this proof, consider this function f such that f of a less than f of b and y belongs to the open interval f of a comma f of b. Now just shift this function f at here in origin, and this function such type g of x equal to f of x minus this distance y. Then g of a equal to f of a minus a, and since f of a less than f of b, that means this value would be less than 0, and g of b equal to f of b minus b, and this value is greater than 0. Therefore, g of a times g of b less than 0, and obviously this function, new function g, is continuous. So by Bolzano's theorem, we can tell there exists at least one point C such that gc equal to 0, and gc equal to 0 means f of c equal to y. Therefore, our proof has done. I hope my all viewers have understood this proof. Okay. Now I will say some nice application of Bolzano's intermediate value theorem. First application. Suppose f, which is defined from closed interval ab to r, be a continuous function, and f attains absolute minimum at the point C, and f attains absolute maximum at the point D, then image of f of AB is equal to f of C comma f of D. For this, consider one new function f from CD to R. Obviously, this is restriction of this function, and this function obviously be continuous, still continuous. Now use the intermediate value theorem. Simple Bolzano intermediate value theorem in a real life. But in functional several variable, this concept is different. Now consider one function. Here, this is very interesting. Notice here f defined, here domain is 0, 1 union 2, 3. Here 0, 1 and here 2, 3. This is the domain. And codomain is real line, and the mapping is defined as f of x equal to 1 when x belongs to 0, 1, and fx equal to 0 when x belongs to 2, 3. If I consider 5 by 2, obviously 5 by 2 here, and half, the point half here, and at the point half, the value of f of half is 1, and value of f of 5 by 2 is 0, and the point 0, between the point 0, 1, there exists a point half. But for this image half, there exists no point in the domain. Okay? So, intermediate value property does not satisfy for this function. But notice, this function is continuous. Continuous because we all of us know definition of continuity. For each epsilon there exists a delta. For each epsilon always there exists, I will get one delta, but this function does not satisfy intermediate value theorem, and this function does not satisfy intermediate value theorem because here the domain is disconnected. So, for functional several variable, these two intervals are disconnected because these two intervals are disjoint. 0, 1 and 2, 3 are disjoint. There exists no continuous path in these two intervals. So, these two intervals are disconnected. In functional variable, there exists one new concept to define intermediate value theorem, and this concept is connected concept. Now I will see the concept connected set. What is the connected set? At first I will see what is the path connected set. Then I will see what is the connected set. A set A is path connected if for any 2 points, but here I have considered it since functional several variable. That means here the point vector for any 2 point which is vector in the set A. Path connected means always there exists a continuous curve containing x and y which is contained in the set A. As for example, consider the set A, and in this set if we consider these 2 points, notice for these 2 points we can draw this path. So this is the path connected. This set is path connected, and this set A is path connected because for every point of this set always we can define one path. So this set A is always path connected set. If we consider these two sets, this is not path connected because if we consider one point here and another point here, we cannot take any path between these 2 points. So this set A and B is disconnected. I hope my all viewers have understood what is the path connected. Equivalent definition of path connected is any 2 points xy belongs to A can be joined by a path. Here we can define a function such type phi from 0 1 to x such that phi of 0 equal to x and phi of 1 equal to y. Okay, this is the definition of path connected. If we can define this type of path, then we can tell this set is path connected, and path connected always imply connected. Path connected, this does not always mean there exists a path. Path may be straight line also. If we consider the set xy belongs to R2 such that x square plus y square equal to 1, consider this circle. This is path connected because if we consider 2 points here, then always I will get one curve in this circle. So this set is path connected, and path connected always imply the set is connected set. Okay? OL. Actual definition of connected set is a set E which subset of R is called connected set if there does not exist two open disjoint set such that it does not contain A union B and A intersection B equal to phi. This is the definition of connected set. To define the intermediate value theorem in functional several variables, at first I will say composition of continuous function is continuous. For this, let xt yt be continuous on the set AB and D be domain in R2 which be the open set such that for any t belongs to closed AB, consider the point xt yt which be the continuous on the interval open interval AB. This is one variable, but here I have considered it xt yt which be the point in the space R2. Consider this curve is gamma. Gamma is be a curve which runs from xt to yt, and the function is such type. For this curve, here this value appears in this curve, in this level curve. Okay? If you know this concept in better way, then you will understand the graph of intermediate value theorem in functional several variable. Now I will say our main goal of this lecture. What is the intermediate value theorem in functional several variable? For short calculation, for easy way to understand, here I have defined the domain in R2. In R2, here the domain. Similarly, this would be for more dimension. Here the domain is not only open, D is also connected set. In functional several variable, this is extra condition. Here the domain is open and connected. Then define a function f of xy from the domain D to R, where domain is open and connected set. Consider this function be continuous and consider 2 point x1 y1 and x2 y2 in this domain, and let z0 be any value between the function f of x1 y1 and f of x2 y2. Then there exists a point x0 y0 in the domain D such that f of x0 y0 equal to z0. Okay? This is the intermediate value theorem in functional several variable. This proof is very easy type proof. Here D is connected set. Therefore, we can find a curve connecting x1 y1 and x2 y2. Here the curve is connecting by the point x1 y1 and x2 y2 in the domain D, which is subset of R2. Now consider a parameter curve gamma, where gamma is given by xt, yt, where t lies between closed A, closed B, closed A and B. Since gamma is a parameter which lies from closed AB, therefore x1 y1 means by this parameter curve at the point A, this is xa, ya, and x2 y2 means by this parameter curve at the point B, this value would be xb, yb. Okay, notice the curve. F of x1 y1 means f of xa, ya, and f of x2 y2 means f of xb, yb. This is look like our previous function. Similar to previous function, we can define f of xt, yt since here phi t. Therefore, xa, ya means phi of a, and phi of a be the function in real variable, and f of x2, y2 means phi of b. And if the function which is defined from x1 y1 to x2 y2, if the function be continuous, then always for any intermediate value I will get one point in the domain. Okay? Phi of A and phi of B is the single variable on the closed interval AB. Thus, by single variable intermediate value theorem, there exists at least one T0 belongs to AB such that phi T0 equal to Z0, and phi T0 equal to Z0 means f of x0 y0 equal to Z0. Therefore, our proof has done. Okay, today I will stop here. In my next video, I will discuss this type of question elaborately. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.